Lecture number 6, Temperature and the Kinetic Theory of the Gases. We have 5 questions: thermal equilibrium and temperature, and the second question, ideal gas law, and the kinetic theory of gases, and we will study mean free path, and the final question, the distribution of molecular speeds. In here, we know and thermal equilibrium and temperature. To measure the temperature of a body, we place the thermometer. The place in the thermometer and mirror of the body. In here, if you want to know the temperature of cup of hot coffee, you stick off the thermometer and the coffee. The two interact. Thermometer becomes hotter and coffee cools off little. After the thermometer settles down a steady value, you read the temperature. And the first and the temperature is rooted the qualitative ideas of hot and cold. This is the sense of tooth. A body that feels not usually and has a higher temperature than similar body that feels cold. And here we take in figure A, and if systems A and B, and here system A and system B, each in thermal equilibrium with the system C in here. And here conductor, and we take, and this is insulator. System A and system B, and conductor in here is this system C. We place a warm copper bar in the close contact with a cold iron, so the copper bar cools and iron bar warms. We say the two bars and thermal contact. The copper bar contacts slightly as it cools, and the iron bar expands slightly as the warm. Eventually, and this process stops, and length of bar remains constant. The two bars and then in thermal equilibrium with each other. And C system of the C initial and thermal equilibrium with both A and B systems, but A, B, and B and are also in equilibrium with each other. This result called a zero law of thermodynamics. And the two systems in the thermal equilibrium, and only they have the same temperature. And two systems in equilibrium only if they have the same temperature. And here, and it would take an insulator and system C, and system A and system B, and resistor and conductor. And system A and B are in thermal equilibrium, which is the other, because in here conductor, and this is conductor. This is here system C in equilibrium with system A and system B, because between two system A and system B consists an insulator. And here and system A and B each thermal equilibrium with the system C in here, and figure A. And here using the constant volume gas thermometer to measure the temperature, and the greater amount of gas in the thermometer, the higher pressure versus time. And here higher pressure and versus time, or versus temperature, and here this is temperature following and degree Celsius, in here following Kelvin scale, and graph pressure versus temperature, the constant volume for 3 different times and quantity of gas. And here there's a plot. This is line, and here this is line. Lots of pressure, the function of temperature for a gas thermometer containing different types and quantities of gas. Dashed line show the plots extrapolated to zero pressure. Extrapolated to zero pressure in here. And the extrapolated plots reach zero pressure at the same temperature minus 273.15 15 degrees Celsius, degree Celsius, and in here this is following. This is point. And the ideal gas is the law. We know the ideal gas. We know the ideal gas law, and this is law. Clapeyron-Mendeleev is a law. Clapeyron-Mendeleev is a law in here. We know, and Clapeyron-Mendeleev is a law. PV and nRT and a number of moles, R universal gas constant, and T temperature measure on the thermometer on the body. And the K in here, but and maybe a number of moles, we know formula and mass divided by molar mass, and maybe we're using a formula and number of moles and number of molecules divided by Avogadro's number. Avogadro's number and replace and here this is formula and formula and gas the gas is low. Gas is low and here K and the constant. K is called Boltzmann is a constant. Boltzmann is a constant. We know 1.38 multiplied by 10 power minus 23 joule divided by Kelvin. And number Avogadro's number 6 multiplied by 10 power 23 and we know and number of moles formula or number of moles and here this is a number of molecules divided by Avogadro's number maybe and here number of molecules equal number of moles multiplied by Avogadro's number and replace in here this is a formula and final formula and PV equal and RT and K in here and A in Avogadro's number multiplied by K, Boltzmann is a constant, equal and universal gas constant. R, this is universal gas constant. We know universal gas constant and 8.31 joule divided by mole Kelvin. In here, this is diagram and plot PV divided by NT in here. This is Y axis, X axis, and pressure for real gases. Maybe and hydrogen gas, oxygen gas, ATC in here, nitrogen gas. And here and this is point following and universal gas constant 8.31 joule divided by mole Kelvin, and this is plot and pressure varied by varying the amount of gas, and then we reduce the density of the gas, and there be by pressure the ratio of PV divided by NT approaches the same value 8.31 joule mole Kelvin for all gases. This value and the universal gas constant. And here this is formula or the ideal gas and is a constant for all pressures. The pressure in here, the volume and temperature of an ideal gas as related by ideal gas law. And the third question and kinetic theory of gases. We should end here. Maybe one system consists different. This is gas molecules and rectangular container. The time interval delta t molecules and the distance velocity multiplied by time interval from right wall will hit the right wall if they are moving to the right in here. To the right, and the pressure in the gas exert on the container is the due collision between gas molecules and the container walls. The pressure is the force per unit area by Newton's second law. This is force in the rate of change momentum of gas molecules colliding with the wall, and here the behavior of gas in thermocroscopic state, variables in here, P and pressure and volume and temperature can be related simple average of microscopic quantities and as the mass and speed of molecules and gas. In here resulting, and this is theory is called kinetic theory of gases. Kinetic theory of gases. We now and the number of molecules on the wall during this is interval and interval delta t, and the magnitude of total change is momentum and p delta p of all molecules during of time interval delta t. To momentum times the number of molecules that in here wall during this interval, and here this is changing momentum, total change momentum, and equal number of molecules divided by volume mv square, a and here area delta t time interval. And we know formula of the pressure and the force divided by area. Force we now and using formula of Newton's second law delta p divided by delta t, and at delta p total change momentum replace in here, and this is formula put on the delta p, and final formula number of molecules divided by volume mv square, and the pressure and here the pressure. And we now put on the pressure multiplied by volume and mv square, and here maybe and here 2n and multiply by 1, and here mv square multiply by 1 divided by 2, and here and the final formula mv square, and here we know mv square average velocity square, and here average velocity square equal 1 divided by 2 kt, and here this is formula following the average energy associated with the motion in the x direction, because in here this is x show you and x direction, and here and the average kinetic energy associated with the motion along x axis in the kt is divided by 2, and nothing special about x direction maybe, and y direction and z direction equal vx square equal vy square equal vz square, and maybe and average square and total velocity square equal and x average x direction, y direction, z direction, and here equal 3v square average. And here and kinetic energy, average kinetic energy of the molecule, the formula 3 kt divided by 2. This is average kinetic energy of the molecules. But in here the total translational kinetic energy of n moles of gases containing n molecules is the formula 3 divided by 2 nRT, and this is number of moles, and here this is formula following kinetic energy of translational for n moles of a gas and gases. Here nk and nk maybe n Na and K and n number of moles, number of molecules, number of Avogadro's number multiplied by Boltzmann is a constant, and here R and number of molecules multiplied by universal gas constant. So, and here this is formula of their average velocity, and magnitude of speed of the molecules in the gas, but in square root formula square mean root mean square in here, and 3 kt divided by mass. Maybe and K we now formula R divided by Na we now, and mass multiplied by Avogadro's number will be molar mass. But we know, and for and the velocity of the sound, and here gamma RT divided by molar mass, and gamma 1.4 for air, because and gamma and adiabatic is a constant. Adiabatic is a constant, for diatomic gas, for air diatomic gas, and 1.4. And mean free path, this is distance between two molecules. Is the average distance traveled by molecule between the collision, and is called mean free path. In here, two molecules, and here this is distance R2 and plus R1, and this is distance and equal D. D and the center, the distance between the third centers, and formula of the mean free path, and final formula 1 divided by n concentration, and P d square, D and the distance between two molecules on the center, and center about the molecules. Okay, in here. Effective diameter of the molecules, but we're using maybe oxygen gases. Effective diameter of the oxygen gases we're using, and lambda. This is formula of the mean free path, and the unit mean free path meter. Okay, and this is formula, and here, and the final formula and correct expression for formula mean free path is given 1 divided square root 2 p n p d square, and here, and we know, and the motion of all the molecules that taken into account, the correct expression for the mean path is given by here. But we know, and here this is figure model of molecule moving with the speed v. In here, this is the direction of the speed in a gas of similar molecules. The time molecules of diameter will collide with any similar molecules whose center and cylinder of volume Pd square and area Pd square, V and T, V this velocity and time, is this principle all molecules and assumed to be at rest. Okay, and for question number 5, the distribution of molecular speeds. We now, and we calculation of the pressure of a gas allow us to calculate the average square speed and the average energy of molecules and gas, but it doesn't will enter any details about distribution of molecule speeds. Before we consider this problem, we discuss an idea of distribution function in general with elementary examples from common experience. And here, this is figure a possible hike in here, distribution function fh and h, and the fraction of the number of hikes between hike and hike plus delta h equals the shade area fh and delta h. The histogram can be approximated by a continuous curve as shown. And here the distribution of molecular speeds, the Maxwell-Boltzmann distribution. We know, and the Maxwell-Boltzmann distribution, and maybe if a gas and molecules, their number and have speed and range, the range between and v plus the v and the n, given by and the n multiplied by f multiplied by dv in here. But this is schematic diagram for determining speed distribution of the molecules of a gas in here. We know, and this is maximum peak in here. This is point following and V maximum and velocity maximum and average. In here, this is average velocity, and root means velocity. Root means speed velocity in here, velocity in here, following this is point. And here this is curve and two curve following and the two temperatures. The first temperature, the first curve and that following the temperature 1, and the second and the second temperature 2, because and this is temperature smaller than and the first temperature the second temperature and larger compare with the temperature 1 and we now formula of the function distribution function in using statistical mechanics. This is a result and Maxwell-Boltzmann speed distribution function in here, Fv and function of velocity and 4 divided by square root and p. M divided by 2kt and power 3 divided by 2 v square multiplied by n exponential power minus mv square divided by 2kt, and this function distribution function of the speed and here and maybe and v maximum and in this is function when and the maximum and 2 and following and speed of maximum and formula 2RT divided by molar mass and for example square root and equal square root 2KT divided by mass of the gas. And here take maximum energy distribution function in here, but we can write in formula and distribution Maxwell-Boltzmann velocity distribution function. We can write and C, and here the C is a constant in here. The energy distribution function is given by in here, but we obtain a total formula and this total formula energy distribution function. Thank you for attention.